In the last few videos, we introduced some general traits of aldehydes and ketones. We looked at some of their practical applications. We also looked at how to name them using both the IUPAC nomenclature system and the common nomenclature system. Now, in this video, we turn our attention to some of the key physical properties of aldehydes and ketones, such as boiling point, melting point, and water solubility. These topics are useful and important because aldehydes and ketones are biologically relevant molecules. And when we think about how these molecules interact with biological systems, such as when one consumes food items that have aldehyde or ketone groups, we need to be able to consider whether we would anticipate the molecule be a solid or liquid as it is metabolized, and that relies upon the melting point of the compound and also on the boiling point. Additionally, when we think about how these molecules interact with the body, water solubility is a key consideration since water is the main substance present within the body. So let's go ahead and take a closer look at how we go about evaluating the physical properties of these important molecules. And yes, there is a reason why I have this melting emoji here. It's to remind us that one of the things we're looking for here is the melting point. So if you feel like you're melting as you're watching this video, you are not necessarily alone. When we're discussing the physical properties of aldehydes and ketones, or any other type of functional group for that matter, we need to focus the discussion on intermolecular interactions, because intermolecular interactions describe how strongly two molecules are attracted to one another, and the more strongly two molecules are attracted to one another, the higher the melting point and boiling point will be, because boiling and melting require disrupting these interactions between molecules using heat as the source of energy to disrupt those interactions. Similarly, solubility also relies upon intermolecular interactions, where molecules will be soluble with one another if they offer similar intermolecular interactions. Hence, like dissolves like. Compounds that have like intermolecular interaction types will be soluble in one another. So compounds that are soluble in water are going to feature intermolecular interactions that allow them to engage strongly with water. So let's go ahead and take a closer look at the types of intermolecular interactions, since intermolecular interactions are what will drive solubility, melting point, and boiling point. When we talk about intermolecular interactions, we are referring to the attraction between multiple molecules, or the interaction between multiple molecules. We talk about the interaction between multiple molecules. We could talk about repulsion, but generally, for purposes of looking at melting point, boiling point, and solubility, we're going to be looking at forces that allow molecules to be attracted to one another. So we're looking at the attraction between multiple molecules. That's why we call it an intermolecular interaction, because inter means between multiple objects. In this case, we're talking about multiple molecules. If we called it an intramolecular interaction, that would be referring to the attraction of the molecule for other components of itself within that same exact single individual molecule. With intermolecular interactions, the general rule that we will see is that the stronger the intermolecular interaction, the higher the melting point, which I'll abbreviate as MP, and the higher the boiling point, which I'll abbreviate as BP. And the reason why this is the case is because melting and boiling require disruption of the intermolecular interaction. And so the stronger the intermolecular interaction is, in other words, the more difficult it is to disrupt, the higher the melting point and boiling point will be, since boiling and melting require disrupting the intermolecular interaction. So, what types of intermolecular interactions should we be focusing on? I'm going to list these in order from the strongest type of intermolecular interaction that we will focus on, going down the list toward weaker and weaker intermolecular interactions. So I'm going to go ahead and draw here along the sidebar an arrow indicating increasing strength of the intermolecular interaction. So I'm going to label this as strength of the interaction. where at the top of the list will be our strongest interaction. At the bottom of the list will be weaker interactions. At the top of our list is the type of intermolecular interaction referred to as hydrogen bonding. This is not a covalent bond or an ionic bond where electrons are shared or transferred fully, but instead it's the strong attraction of a negatively polarized oxygen or nitrogen atom with a very positively polarized hydrogen atom that is bonded to an electronegative atom. So in other words, when we have a hydrogen that is directly bonded to an oxygen or a nitrogen for that matter, I'm going to plug in an R group here to represent whatever variable group you want to have in place there. The bond between oxygen and hydrogen is very polarized, with the oxygen atom taking the lion's share of the electrons from that bond. To become negatively polarized, the hydrogen takes on a very positive polarization, because when the electrons are not evenly shared in this covalent bond, that's going to cause the atom that has more electron density to be negatively polarized. This isn't a full negative formal charge, but it's a strong polarization of this bond where the electrons are unevenly distributed across here, and they're residing mostly under the jurisdiction of the oxygen atom, making that oxygen negatively polarized. So what happens is if you have multiple hydroxy groups present within a container, and we go ahead and line these up here, as will happen, what we find is that the very negatively polarized oxygen atom is strongly attracted to the positively polarized hydrogen atom. And we show this with the dotted line here. So I'm showing two hydrogen bonds, as we call them, these strong intermolecular interactions between the positively polarized hydrogen and the negatively polarized oxygen here and here, representing a very strong attractive force. And that force is very strong because of the fact that this bond is very, very highly polarized, because there is such a large electronegativity difference between oxygen and hydrogen within these structures. So the hydrogen bond I can write out in words here and define as the attraction of a negatively polarized, so I put delta negative for negatively polarized oxygen, or a nitrogen for that matter, with a positively polarized hydrogen atom that's bonded as well to an electronegative atom there. So this is going to be our strongest of the possible intermolecular interactions that we will talk about. In the case of aldehydes and ketones, our relative groups that we are focusing on here in this chapter, with an aldehyde or ketone, we have a carbonyl group, like so, with an R group on both sides, where R is a carbon or a hydrogen. One of those two groups would be a hydrogen if it's an aldehyde. Both would be carbons if it's a ketone. And what happens in the case of these molecules is that we observe that aldehydes and ketones can't hydrogen bond with themselves because there is no OH group here. An OH group is required for hydrogen bonding with itself, like we saw over here, where we had the negatively polarized oxygen interacting with the positively polarized hydrogen. So if you have a container that is exclusively aldehydes or ketones, there's no OH or NH groups here to interact. There's just oxygen atoms. But what can happen in the case of mixing aldehydes or ketones with water is there can be an intermolecular interaction between the hydrogen atom of water, because that is strongly positively polarized, and the oxygen there is negatively polarized, with the oxygen atom of our carbonyl group, because the oxygen atom of our carbonyl group is negatively polarized since it's bonded to an atom that is less electronegative than oxygen. So what you can get is a form of hydrogen bonding here, as we show with our dotted line there, representing our hydrogen bond. So while aldehydes and ketones can't interact with hydrogen bonding amongst themselves, if you put them in a container of water or a container of alcohol, they can hydrogen bond with the hydrogen atom from that alcohol or water molecule, because that hydrogen is directly bonded to an electronegative atom. So hydrogen bonding can come into play as an important factor in determining the water solubility of aldehydes and ketones, because it will drive how aldehydes and ketones interact with water and with alcohol. So that's our strongest intermolecular interaction that we will look at going down the list to the next weakest intermolecular interaction on the list, we have our so-called dipole-dipole interaction. Dipole-dipole interactions also rely upon the fact that bonds are polarized, meaning that the electrons are unevenly shared within the bond. Hydrogen bonding is an extreme example of that, where we have an oxygen and hydrogen bonded with very different electronegativities. Dipole-dipole is really anything else where we have bonds where the electrons aren't completely equally shared, and as a result of the polarity difference between the atoms being less than in the case of an OH group or NH group for hydrogen bonding, what we find is that dipole-dipole interactions are weaker than hydrogen bonds. That's why they're down the list here. So dipole-dipole interactions are going to represent the attraction of partially positive atoms and partially negative atoms to one another. And this is excluding the special case of hydrogen bonding, where we can think of hydrogen bonding as a special, extremely strong example of a intermolecular interaction. Dipole-dipole interactions come into play anytime we're dealing with molecules that have an uneven distribution of electrons due to one atom being more strongly electronegative than the other. For example, in the case of aldehydes and ketones, again here R is going to represent a hydrogen or a carbon atom. And in the molecule, what we find is that the oxygen is more electronegative, so that takes on a negative polarization. Carbon is less electronegative, so carbon is going to be positively polarized, meaning the electrons aren't evenly shared. And what happens in a dipole-dipole interaction is that when this molecule comes into close proximity with another ketone or aldehyde molecule, such as what I have drawn here, the second aldehyde or ketone molecule can engage in a dipole-dipole interactions via the negatively polarized oxygen atom of one molecule with the positively polarized carbon of another, such as what we see here with my laser pointer, with the positively polarized carbon of one aldehyde or ketone interacting with the oxygen atom of another. This is a weaker interaction than a hydrogen bond because the carbon atom and oxygen are not as strongly polarized as an OH or NH bond in the case of the hydrogen bond. So a dipole-dipole interaction is a weaker version of a hydrogen bond that relies on some of the same principles, that it's the attraction of positively polarized and negatively polarized atoms, but it's a less extreme example. Hydrogen bonds are very strong and very extreme examples of interactions between different molecules with OH or NH groups. Dipole-dipole interactions are these types of engagements of positively and negatively polarized atoms, but much weaker than a hydrogen bond, and hence less influential on the melting point and boiling point of molecules. So in other words, if a molecule is capable of engaging in both dipole-dipole interactions and hydrogen bonding, the hydrogen bonding is going to be the more important consideration when we start to think about what is the melting point and boiling point of the substance going to be. And then finally, lacking hydrogen bonding or strong dipole-dipole interactions, what comes next on the list are what are referred to as van der Waals forces, or London dispersion forces is another term that you may have seen used to describe these. So these van der Waals forces or London dispersion forces arise from so-called electrostatic attractions between atoms of nonpolar molecules. So when we talk about nonpolar molecules, what we're referring to is molecules where there is not a strong electronegativity difference between atoms, so the atoms are relatively equally shared in covalent bonds, but nonetheless, there is still a pretty low-grade attraction between atoms within these nonpolar molecules. So van der Waals forces, written out in words, is our electrostatic attraction that occurs between atoms of nonpolar molecules. Or atoms of nonpolar bonds. The most prevalent example of a nonpolar bond that we come across within the field of organic chemistry are carbon-hydrogen bonds and additionally carbon-carbon bonds. So in the case, for example, of alkanes, if we had a couple of different 4-carbon alkanes here, there are van der Waals forces that attract these molecules electrostatically to one another, but this particular interaction is weak relative to dipole-dipole interactions or hydrogen bonding interactions. And furthermore, if the molecule is branched, meaning the atoms aren't all part of a chain that's linear, but instead some of the carbons branch off as methyl branches, alkyl branches, or whatever else, branching is going to decrease the strength of these forces and hence decrease the intermolecular interactions. So we can add that as an addendum here under our van der Waals forces that we're going to decrease the interaction if we increase the branching of the molecule. And the reason why we decrease the interaction if we increase the branching is we don't allow the molecules to pack together as tightly. So here in our two butane molecules, we see that they can line up so they're fairly tightly packed. If we envision instead of having this nice straight chain for each of these, we took one of those carbons and made it into a branch, the molecules would not be able to pack as tightly together and hence would not be able to engage in as strong of electrostatic interactions. And by lowering that interaction, we would in turn lower the melting point and lower the boiling point, because intermolecular interaction strength is what's going to drive the melting point and boiling point. So let's go ahead and take these principles that we've just looked at to think about the implications of this on melting point, boiling point, and water solubility of these compounds. I'm going to go ahead and zoom out here of this information so that we can have it kind of small up in the corner of the screen to use, but focus on some example problems here. So let's take a look at the implications of these intermolecular interactions and apply that toward some example problems. First off, when we think about the chain length of an aldehyde or ketone, what would we expect the relationship between chain length and the water solubility to be for aldehydes and ketones? So I'm going to look at the relationship between the carbon chain length and water solubility for aldehydes and ketones. Keep in mind, like dissolves like, so the more similar in intermolecular interactions the aldehyde or ketone is to water, the more water soluble it is going to be. What happens with aldehydes and ketones is that if we have relatively short R groups here, so R equals a hydrogen or a short carbon chain, then the bulk of the type of intermolecular interactions that will go on are going to be dipole-dipole interactions, where we would have the negatively polarized oxygen atom interacting with positively polarized atoms. And additionally, that special type of dipole-dipole interaction is really strong called a hydrogen bond, where the carbonyl group oxygen can engage in a hydrogen bond with the OH hydrogen atom. And so if we have a very short alkyl chain here or here on our aldehyde or ketone molecule, then the predominant interaction that's going to be able to occur will be a hydrogen bond between the oxygen atom here and the OH group of water. And so that's going to increase the water solubility because it's going to increase the likeness between the two structures, between the aldehyde or ketone and water. However, as the chain gets longer, that's going to result in the aldehyde or ketone being less like the water molecule, because you're going to be increasing the extent of van der Waals type forces between the nonpolar parts of the molecule, and you're going to be decreasing the extent of how strongly the hydrogen bonding is driving that interaction. And so as a result, the relationship between the chain length of an aldehyde or ketone and the water solubility is that as the chain length increases, we're going to decrease the water solubility. As a general rule of thumb, we will find that aldehydes and ketones that have carbon chains of less than approximately 5 carbons are water soluble. If we go much above 5 carbon atoms, we are going to find that the molecule is not soluble in water at all. What about the relationship between the chain length of an aldehyde or ketone and its melting point and boiling point. So the relationship between the aldehyde or ketone chain length and boiling point and melting point. And I cover those together because if the melting point is higher, the boiling point will also be higher, since both of those are driven by the intermolecular interaction strength, where the stronger the intermolecular interaction that's going on, the higher the melting point and boiling point. So with regard to the chain length of aldehydes and ketones, as we increase the extent of intermolecular interaction between one aldehyde molecule and another, we're going to increase the melting point and boiling point. As the chain length increases amongst these molecules that are all in a container together with other aldehydes and ketones, that's going to increase the extent of van der Waals forces within that container. We also have dipole-dipole forces going on between the carbonyl group oxygen and the carbonyl group carbon, because those are strongly negatively polarized on the oxygen, as we see with my laser pointer on the left side of the screen, and positively polarized with the carbon. So as the chain length increases, we're going to see that the intermolecular interactions increase, and that's going to cause the melting point and boiling point to increase as well, because the longer the carbon chain, the more van der Waals force interactions there will be, because the longer the carbon chain, the longer this network of interaction can be between atoms of nonpolar bonds. And also throughout this, we will have within each molecule the opportunity for a dipole-dipole interaction that remains there as well. So you could think of the van der Waals forces and the dipole-dipole interactions working together to raise the melting point and boiling point of these compounds, because in the case of short chain compounds, dipole-dipole is really the only force that we have to much extent, and then as the chain length gets longer and longer, the van der Waals forces become more and more significant. So the relationship between the chain length and melting point or boiling point is that as the chain length increases, what we will see is that the melting point and boiling point go up as well. What about another example problem where we're going to look at establishing the trend in melting point and boiling point? So what is the trend of increasing melting point and boiling point for molecules of a similar molecular weight? So in other words, a similar size, similar number of carbon atoms, for example. What is the trend of increasing melting point and boiling point for molecules with similar molecular weights and the following functional groups? So we want to organize these in order from the lowest melting point and boiling point to the highest melting point and boiling point. The ones that we are going to focus on here are alkanes with just carbon-carbon bonds and carbon-hydrogen bonds, aldehydes and ketones, which I bucket together since they have very similar properties due to having a carbonyl directly bonded to either exclusively carbon atoms or carbon atoms on one side and a hydrogen on the other in the case of aldehydes, and then alcohols. In order to evaluate the trend in melting point and boiling point for these three different functional group types, or four different functional group types if you want to consider aldehydes and ketones separately there, what we find is that we need to evaluate the types of intermolecular interactions that go on in each of these molecules to compare what we would anticipate their melting point and boiling point to be, where the stronger the intermolecular interaction that is in play, the higher the melting point and boiling point will be expected to be. So evaluating these three, alcohols are the only one of the three that will hydrogen bond amongst themselves. Aldehydes and ketones can engage in hydrogen bonds if they are mixed with water or mixed with alcohols, but when they're in a container by themselves, melting or boiling, they don't have the opportunity to hydrogen bond. And so alcohols are the only type of molecule here that will hydrogen bond. So when we're considering apples to apples, meaning look at molecules with similar molecular weights, when one of those three types of molecules is able to hydrogen bond and the others are not, since hydrogen bonding is the strongest of the interactions, we're going to expect that that will confer the highest molecular melting point and boiling point. So I'm going to go ahead and tag alcohols as the highest melting point and boiling point here. And then working our way down the list of strength of interactions, as we look at alkanes and aldehydes and ketones, we saw that aldehydes and ketones weren't able to hydrogen bond with themselves, but they were able to engage in dipole-dipole interactions like we saw here. And dipole-dipole interactions are stronger than van der Waals forces, and so therefore aldehydes and ketones that can engage in dipole-dipole are going to have the middle of the road melting point and boiling point. So I'm going to put those in second place of the three types of molecules that we're evaluating here. And then alkanes can't engage in dipole-dipole interactions because they don't have positively and negatively polarized atoms to a significant extent, and they certainly can't engage in hydrogen bonding. And so what we're left with is just van der Waals forces, which are the weakest of these three types of interactions. And so with van der Waals forces only, and van der Waals forces being the weakest intermolecular interaction, that is going to cause alkanes to have the lowest melting point and boiling point, because it's very easy to disrupt the interactions between those molecules since they're interacting very weakly compared to the other molecules that have a similar size, meaning similar molecular weight here. With these general examples in place, what we will do in the next video is tackle a couple of example problems where we look at specific molecules that represent these different functional groups and compare and contrast the expected boiling points, melting points, and water solubilities for those to apply what we've learned here in this video and apply these general examples toward some more specific situations. Stay tuned.